Okay, let's get the rest of the study guide done. Alright, so an object has 400 kilograms of momentum. If it comes to a stop in 0.8 seconds, how much force must have been applied to it? So this is where we use impulse equals change in momentum, or force times time equals change in momentum. Okay, and they don't give us the mass and velocity, but they give us the total momentum. Okay, so it has this much initially, and then it comes to a stop. Okay, and it does that in 0.8 seconds, and we're looking for force. So force times 0.8 seconds would be final 0 minus initial 400. That's my change in momentum, because it started at 400 and then it came to a stop. Okay, and then I just need to divide both sides by 0.8, because 0 minus 400 is minus 400. The minus is there because of the direction of the force. Force is a vector, so let's see, 400 divided by 0.8 is 500 newtons. Okay, so the force is 500 newtons. And you can leave the negative if you want, because that's just showing us the direction of the force. That means that could have been like a braking force, maybe. Maybe this is an object where somebody was putting on the brakes, and so the force direction is going to be opposite the motion, because we're trying to stop the motion. In terms of impulse and momentum, explained by why airbags are added to cars as an important safety measure. So this goes back to force and time. Okay, so let's say we've got our steering wheel. Okay, and then we've got an airbag, which is like a big, and those do explode out with some force. Okay, but what we're thinking about is not so much that as we are the comparison between hitting your face on this, the hard plastic steering wheel, versus this, a pillowy or more pillowy airbag. Okay, so in terms of impulse and momentum, like when you have an accident, you're going to come to a stop. So your impulse equals your change in momentum. You're driving this car, it's got a mass, you're driving at a certain velocity. Whether you have an airbag or not, your change in momentum is going to be the same. But it's this force versus time combination that can be different. So if we have no airbag, this is where we have a large force over a short time. Okay, you're going to have a large force when you hit this steering wheel with your face and no cushion, and a short time in which that, a really short time in which that impact, that force occurs, because car crashes happen really fast. You know, a lot of times we don't even know that there's going to be a crash, and then it happens. If you have an airbag, so there's an impact and then the airbag inflates instead of nothing and your face just hits the steering wheel. When the airbag inflates, there's a weaker force of impact because there's something to cushion that impact, and then a longer time. It's going to be a longer time over which your face impacts with the front of the car because the airbag's in the way. So airbags will provide a cushioning between you and the car and protect you more. Okay. Airbags still, they still do damage. They still cause bruises, but there's much less damage that occurs than would be if you didn't have it there. And we'll talk about that this week. There's a couple of videos that we'll watch. Not anything graphic, just how they work, how they protect us. So, okay, 2,000 kilogram truck traveling at 15 meters per second hits a pile of marshmallows and comes to a complete stop after 1.5 seconds. So, a realistic scenario. Okay, so what's the initial momentum of the truck? Well, it has a mass of 2,000 kilograms, and it's traveling at 15 meters per second. So its initial momentum is 2,000 times 15. Hang on, I'm having to use my phone because I don't know where my calculator is. I guess it's in my bag, but I don't know where my bag is. Okay, so 30,000 kilograms times meters per second. How much force is needed to stop the truck in 1.5 seconds? So this is our force times time equals mass times final minus initial velocity. This is our change in momentum. Okay, this is an equation I tried to get us to practice with on Thursday. So we're looking for force. Force equals 1.5. I think this might actually have been one of the problems I gave y'all. 2,000, it comes to a stop, so final velocity 0, minus 15 is the initial velocity, okay? So I need to multiply 2,000 times 15. That's going to give me 30,000, which is a similar number to what I see up here. And then I divide that by 1.5. So my force here is 20,000 newtons that I need in order to stop the truck. And so these givens, this is time, this is mass, this is final velocity, this is initial velocity. I'm using impulse equals change in momentum to solve for force here. What's the truck's change in momentum? Well, the initial momentum was 30,000. The final momentum was 0 because it came to a stop. So its change in momentum is minus 30,000 kilograms times meters per second. It basically started with this, it ended at 0 because it came to a stop. And this quantity equals, when we multiply these out, that gives us the same quantity, the minus 30,000, because impulse equals this change in momentum. So I'm going to put that just to emphasize. Okay, what is true about the total momentum before and after these objects collide? So we've got two objects, and let's see, if we calculate their momentum values, their mass times velocity, we got 12 plus 1 equals 3 plus 10, 13, 13. So total momentum is conserved. Initial momentum equals final. Okay. And then during a collision between two objects, one object loses 10 kilograms of momentum. What happened to it? What must be true of the momentum of the other object? So as long as we're a closed system, the lost momentum is transferred to the other object. Okay, and so the other object must have a larger final momentum. And the bowling example on the first page is an example of that. Okay, so we have the bowling ball and we have the pin. The pin started off at rest. The bowling ball started off with a momentum of 25. They hit each other. The pin gained momentum. It gained up to 20 kilograms of momentum. The bowling ball lost 20 kilograms of momentum. The bowling ball basically transferred its momentum to the other object, the pin, and so the other object ended with a larger final momentum. Our totals are still the same. Sometimes it's hard to make sure we understand that, because you have these individual values, but then your total is conserved. It's like with energy, your potential and kinetic can change, but above that, like that bucket of energy I talked about, that total mechanical energy has to stay the same. Okay, hope that helped.